Hello, Honors Chem students. Mr. Keister here with you again today. This is the video for Wednesday, September 23rd, 2020, which is our scheduled 24th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do-nows, today's schedule. Today you're going to be picking up Lab Activity 2-1 Part C, which is over gas behavior. I'm going to base this off the premises of the kinetic molecular theory, which we've been discussing here recently. Your homework for today was to complete Lab Activity 2-1 Part B, okay, which had to do with, we talked about kinetic molecular theory, we talked about pressure, what gas pressure is, what atmospheric pressure is, and we talked about how to do pressure conversions. We looked at both a barometer and a manometer yesterday, so hopefully you're clear on how those work and what they tell us. I'm not collecting 2-1B, but I certainly want you to check your answers and make sure you did all that correctly. That's important to know that stuff. They're posted on the backboard, of course. They were at 7 this morning. They're also posted in Canvas on my answer keys page if you are at home. Today we're going to look at 2-1 Part C, which summarizes our discussions on gas behavior. This involves working with an online gas behavior simulator on the front board here, so I'll be kind of running back and forth between the board and my desktop computer. So we're going to illustrate the gas behavior relationships, which I think you will then be much clearer on why gases behave the way they do. So let me get over to the desktop and change the board. Okay, I'm going to cut one of the lights off here so we can see when we have the simulator on, it'll maybe can show up a little bit better. Take that up a little bit. So you have 2-1 Part C in front of you. Let's take a look. So in this activity, we're going to be exploring the relationship between pressure, volume, temperature, and amount of a gas, or number of particles of a gas. We're going to use a simulation from the University of Colorado to explore these relationships at the particle level. You can access this site directly on your own Chromebook. The link is listed here on the paper that you have in front of you. First thing I probably want to remind you is we're going to look at both some direct relationships and some inverse relationships. So if you remember that directly proportional of two variables are directly proportional, remember that means that the ratio of the two is a constant. Meaning if one goes up, the other goes up by the same amount. If one goes down, the other goes down by the same amount. So whatever one does, the other does the same thing. So same effect. If two things are inversely proportional, we said that their products are a constant. Meaning if one goes up, the other goes down, okay, by its inverse, basically, all right? So if one goes up, the other goes down, one goes down, the other goes up. And so the effect on one from the other is the opposite effect. Okay, opposite effect. So the first one we're going to look at is pressure versus volume, okay, pressure versus volume. So we will change the volume of a gas and measure the effect on the pressure of the gas. The temperature and the amount will remain constant. So let me pull up the simulator and we'll take a look at that. So you'll hear me talking, hopefully, but we'll be showing the simulator here on the board. All right, so here we have this here. So as you can see, we have a container here. We have a little air pump that allows us to pump some gas particles. I assume it's air. Gas particles in here. We've got a temperature gauge up here. We have a pressure gauge here. And we have the ability to increase or decrease the temperature down here below. So let's see. First up, we are going to hold the temperature constant. Hold the temperature constant there. Give it a few more pumps. And as you can see there now, gas particles move randomly in straight line motion. All right. They collide with each other in the walls of their container, and the force and quantity of those collisions is what causes gas pressure. So if you look on the pressure gauge here, it's showing about 20 atmospheres. Okay. So now what we're going to do is increase the volume. All right. So I'm going to make this container bigger. All right. And now, so we've got more room in there. So what's happened to the particles? Collisions. Well, the collision rate's gone down. All right. There's more room in there, so the spacing is increased and the number of collisions is decreased. And if you look at the pressure gauge here, the pressure has gone down. So as volume goes up, pressure goes down. Well, let's make the volume smaller and see what happens. So look here. So now we've got a much smaller space, all right? So the spacing is decreased, meaning the particles have increased their collision rate, and obviously the force, the number of collisions has gone up. And if you look at the pressure gauge now, it's shot way up to 36 atmospheres. So again, as you can see there, as pressure goes, as volume goes up, pressure goes down. As volume goes down, pressure goes up. All right, so let's get back to our paper here, and we'll fill that in. All right, so when the volume increased, of course, the pressure decreased. All right, the pressure decreased. This is an inverse relationship, all right? Whatever one does, the other does the opposite, all right? So let's see then. So we're going to draw a graph to represent this relationship, pressure on the y and volume on the x. So here we go, little graph here, pressure on the y, volume on the x. All right, so let's see here. Inverse relationship. You remember how that graphs? All right, it's a hyperbola, like so. So as you have various points on here, see up here, pressure is high, volume low. Pressure has gotten lower, volume higher. Pressure even lower, volume even higher. All right. So this then obviously the volume. If the volume can change, we're talking about a flexible container. You know, such as a balloon. A balloon's a flexible container. All right. So we said that pressure and volume are inversely proportional. If one goes up, the other goes down. All right. And this, my friends, is one of our basic gas law behavior relationships. The person that studied this effect, the effect of these two variables on each other, his name was Robert Boyle. And this is known as Boyle's law. Volume and pressure are inversely proportional. Right? That is Boyle's law. Okay, so let's do a little particle diagram here of the conditions that we have been witnessing here. So initially, remember, I had a lower volume, a smaller volume, and then I made the volume bigger, all right? So smaller box here, larger box here to represent volume. So we kept the number of particles the same, so I'm just going to draw a couple, all right? Of course, you increase the volume, the spacing got bigger, right? Spacing got bigger, remember that? So we're showing the difference in the spacing here. So here the volume was lower, meaning the pressure was higher. Here the volume was higher, and thus the pressure, oops, that should be higher, sorry. The pressure was lower. Now, how can we show the fact that the collision rates changed? Okay, so here I'm going to show, remember on the other day I said, well, we need to kind of, on our particle diagrams, get a little more specific and show the speed of the particles. Okay, so I'm going to give both of these situations one little bar or one little tail of speed to show that the speed has not changed because we kept the temperature the same. Remember, speed is influenced by the amount of energy the particles have, the temperature being the same, the amount of energy is the same. So I'm going to show them both having one tail or one bar of speed to show that they're the same. Now, in a larger container, we're going to have fewer collisions. I'm going to designate a collision by just putting an arrow on the end of that tail or bar to show that it's colliding here with the walls of the container or with each other, either one. And so in a smaller volume, the pressure is greater, meaning there are more collisions. So to illustrate that here, I'm just going to add a second collision. Doesn't matter what direction you go with it. All right, but I'm just going to go ahead and show that. So here I'm showing one collision per particle. Here I'm showing two. Now it may be different than that, of course. We're just trying to show the difference. All right, we're just trying to show the difference. So smaller volume, greater number of collisions, greater pressure. Larger volume, smaller number of collisions, smaller pressure. And it graphs a hyperbola. Right? This is Boyle's law. Volume and pressure are inversely proportional. Okay? All right, let's look at the next one. So the second one is we're going to look at, there we go. Let's clear this out, okay? We're going to look at pressure versus number of particles, all right? Pressure versus number of particles. So now we're going to leave the volume the same, okay? Guess I could erase my stuff here. Let's see that better. There we go. All right. So I'm going to keep the volume the same now, and I'm going to put in, let's see, a couple of pumps of particles there. Give them a chance to do their thing here. So again, random motion, straight line, and we get a collision rate now, and it looks like the pressure gauge, it's settled in somewhere around 11 atmospheres, or 11 ATM. All right, so now so now we have the volume constant, right? We have a rigid container like a tank or, something like that. So now I'm going to add more particles. What do you think is going to happen? Put in about 3 more pumps, all right? More particles, more collisions. More collisions, higher pressure. All right, so now look, the pressure shot up to about 29 ATMs. All right, so here we're keeping the volume and the temperature constant. All right, but now we've just changed the number of particles. And as you can see, more particles means more pressure. Now that's not an inverse relationship though. What is it? It's a direct one. All right, it's a direct one. All right, so let's I'll go ahead and clear that out. Let's pull our document back up here. Scoop that up to number 2. Okay? All right. So now we saw that when the number of particles increases, the pressure also increases. All right? And of course, this then would be a direct relationship. All right? So do you remember how we graph a direct relationship? All right, so we have a number of particles. We'll call that N, all right, on the x-axis and P on the y. And as we increase the number of particles, the pressure then, of course, increases. Remember how a direct relationship graphs? Remember density was one. If you said straight line, positive slope, you're right. That's exactly what it is. Now, will this graph run through 0, 0, run through the origin like a density graph does? Well, think about it. If there are 0 particles, how much pressure are you going to get from the force of their collisions? Well, if there's no particles, there aren't going to be any collisions. So if you said 0, 0 is a valid point, you're absolutely right. It is. All right? So 0, 0, valid point. And remember, it graphs a straight line, positive slope. Now remember, this is a rigid container. The volume is constant. All right, the volume is constant. The person who discovered and studied the relationship between pressure and number of particles was a person you probably heard of. We got a number name for him. His name was Amadeo Avogadro. This is Avogadro's law. Okay. Pressure and number of particles are directly proportional. If one goes up, the other goes up as well. All right, Avogadro's law actually has 2 scenarios. All right. We mentioned the one, pressure and number of particles are directly proportional. Okay, that's if we have a rigid container like we do here. Now, if the container is flexible like a balloon, think about it. So when you blow up a balloon, what are you doing? You're adding more particles to it, right? You're adding more CO2 as you exhale into it. If the container is flexible like a balloon is, what happens to the volume of the container when you add more particles? Well, pretty apparent. What happens to a balloon when you blow it up with every breath? It gets bigger, right? So if we have a flexible container, then volume and number of particles are directly proportional. Again, we're keeping the temperature constant on all this, okay? So Avogadro's law basically is 2 statements depending on whether or not your container is flexible or not. So we could graph number of particles and volume as well. It graphs exactly the same. Right? It graphs exactly the same. So let's look at our situation here with a rigid container. All right. So again, as you have various points along the way, of course, 0, 0 is there. And as you increase the number of particles, pressure goes up by an equal value. Okay. So let's show that in here. So initially, I'm just going to throw a couple of particles in here. And this is with a smaller number of particles and a smaller pressure. Okay, smaller pressure. There we go. So I'm going to give them a collision. I'm going to give them 1 bar or 1 tail of speed. Here again, we haven't changed the speed. The temperatures remain the same. So over here, we're going to remember to keep the speed the same. So now what do we do? Now we increase the number of particles, and so the pressure went up now. Okay. There we go. So I'm going to throw in a few more particles. All right. Now, how are we going to show this? So I'm going to give them the same speed. I'm going to give them a collision. All right. Now take a look at that. Are we showing up here? We showed more collisions or fewer collisions by a different number of arrows, attached to the particle. I want you to notice something here. There's actually 2 ways we could do this. Right now, already, are we showing more collisions over here than we are here? And the answer is yes, we are. I see 4 collisions there. I see 2 here. I would accept this as a acceptable diagram showing Avogadro's law here. Of course, again, we have a rigid container in this case. The size of the box is the same. However, in reality, as we saw on the simulator, as we add more particles, the number of collisions per particle also increases. So just as acceptable, maybe even more so, would be showing an extra collision on there. I'm going to accept either way, all right? Both of them show an increase in collisions, which would result in an increase in pressure. So I'm okay with either one of them. In reality, this one's probably a little better because there are going to be more particles, more collisions per particle when you add more particles to the same space. Okay? So there is Avogadro's law. Here we're showing a rigid container. If we were showing a flexible container and we increase the number of particles, the volume would go up, all right? Number of collisions, of course, goes up with more particles, but the volume now is going to go up since the container is flexible. And again, that's evidenced by when you blow up a balloon. Okay? All right, move on to the next one. Go ahead and erase this first, and then pull the simulator back up. Move it up here to number 3, and we'll pull our simulator back up. Okay, so now number 3, we're going to change the temperature of the gas, and we're going to leave the volume the same, so we're going to have a rigid container. So let me put some gas particles in here first. Cause several bumps there. So we're going to leave the volume the same, but now we're going to change the temperature. All right, so if we increase the temperature, we're going to put more energy in the system, and the particles are going to absorb that energy, and what are they going to do? Well, if you said they're going to move faster, you're absolutely right. So let's do that. So I'm going to turn on the heat down here. I got a heat and a cold bucket. I kind of like that. Didn't know we had one that could do both. So let's crank up the heat here. Oh, well, there's a little flame there. And if you look up here, you can see the temperature. Look up at the temperature gauge. It's going up. Look at the particles. What are they doing? All right, what are they doing? They are moving much faster, which means they're colliding much more. And we're getting there a very big increase there in pressure. That pressure is just skyrocketing, all right, as you can see. There we go. That's a good one. I like that one, all right. Of course, the lid hasn't blown off yet, thank goodness. You know, you can only increase the pressure in a rigid container so much. Let's see, what's a good example of this? Oh, I just thought of one. Have you ever thrown an aerosol can into a campfire? Even an empty one. Well, let me tell you something. An empty aerosol can is not empty. There's still, you know, a can of hairspray, when it's out, there's still gas in there. There's just not enough to shoot it out the top. Well, you throw an empty hairspray can in a campfire, you better stand back, because as you increase the temperature rapidly, and those gas particles in there start jumping around a lot quicker, and they exert a greater pressure on that can, it can only take so much. And as some of you probably already know, it will explode due to that increase in pressure. All right, so let's take a look at this with our diagrams here. So when the temperature increased, the pressure also increased, which again is a direct relationship. The person who studied this relationship between pressure and temperature in a rigid container, he was a Frenchman named Joseph Louis Gay-Lussac. All right, love that name, great name. French have good names. All right. This is known as Gay-Lussac's law. Gay-Lussac's law. All right. Pressure and temperature are directly proportional. Joseph Louis Gay-Lussac. All right. So if it's a direct relationship, all right, how's it going to graph? We'll put P here and T here. It's going to graph a straight line, positive slope, like any other direct relationship. Now, Let's talk about, does it run through the origin? Of course it does. All right. But now let's think about that. Let's go ahead and draw it. Of course, we got various points here. And it runs through the origin, no doubt. But let's talk about this temperature. All right. 0. Are we talking about 0 Fahrenheit? All right. That's pretty cold. But do particles move at 0 Fahrenheit? Yes, they do. Witness what happens when it's 0 outside in the wintertime. Are things still moving around? Sure they are. All right. Is it 0 Celsius? No, it's not that either. What's the 0 at which there is no energy whatsoever? None. And if you said 0 Kelvin or absolute 0, you're absolutely right. So this is 0, but it's absolute 0 or 0 Kelvin. All right? Absolute 0. 0 Kelvin. So this temperature is on the Kelvin or absolute scale. All right? So let's, these are directly proportional and up and up. So initially, we started at a lower temperature, so T was lower and pressure was lower. So I'm going to just throw in a couple of particles here, give them 1 bar or 1 tail of speed, and give them a collision. Now, with an increase in temperature, again, this is a rigid container. Right? This is a rigid container. When we increase the temperature, pressure, of course, went up. But what happened to the speed of the particles? What'd you see? Oh, they increased their speed dramatically, right? Okay, well, we got to show them moving at a greater speed now. So we kept the number of particles the same. We didn't add any particles. Let's give them 2 bars or 2 tails of speed now, all right? To show that these guys are moving faster than they are over here. And also with an increase in pressure, you saw this on the simulator, not only does their speed go up, but their collision rate goes up, which is what causes the increase in pressure. So let's give them another collision too. So I'll just give them another one like so. Again, the direction there doesn't matter. All right. So there we're showing it. Particles the same, volume the same, rigid container, increase the temp, speed goes up, collision rate goes up, pressure goes up. Avogadro's law, all right? Pressure and temperature, although now we've got a little more specific there, pressure and Kelvin temperature are directly proportional. Okay? Good deal. One more to go. All right. Number 4 is volume and temperature. This is in a flexible container. Flexible container. All right, so let's pull up the simulator here. Okay, there we go. And I'm going to go ahead and put some particles in there. Give a couple of pumps here. All right. But now I'm going to increase the temperature. All right. Again, like we did before. And we're going to keep the pressure constant here. All right. And now let's increase the temp and see what happens. There we go. Let's turn up the old heat here and see what happens. All right. Oh, look already. As I increase the temperature and the particles are moving, pressure, volume too large. Yeah, I know. Let's start her back here again. And I have to watch quickly, all right? So here we go. We've got a flexible container, same number of particles. Watch quickly because this goes fast. As we increase the temperature and the particles move faster and the container is flexible, what happens? There we go. Particles faster, more collisions, and now the container is getting larger. All right, volume is increasing with an increase in temperature. Basically, what does that mean? Well, in a flexible container, it can only increase in volume so much. So what's going to happen to it? It's going to burst, right? It's going to burst. So there we go. All right, good deal. You probably noticed this. So here's an example. Let's say you blow up a balloon in the room, all right, inside. And you take it out in your car and you forget about it and you leave it in the back seat and it gets cold overnight, kind of like it did last night, all right? It got cold overnight. You go out in your car the next morning and you look at the balloon and the thing looks like it deflated. Well, it doesn't mean you tied a bad knot, all right? It just means that the particles slowed down, okay? And since that balloon is a flexible container, its volume increased, or decreased, got smaller, all right? Now, if you had blown up a balloon outside on a winter day, all right, outside in the cold, and you bring it inside, what's it going to do? Well, as the temperature warms up, those particles, and they increase their speed, since it's a flexible container, the balloon's going to get bigger, all right? The balloon's going to get bigger. So, again, this is with a flexible container now, all right? So, when the temperature increases, now the volume increases. Again, this is a direct relationship. So here we go. Here's T, here's V, all right? Gonna do this again, same thing. Now we got a flexible container. Flexible container, all right? This is still 0 Kelvin, or absolute zero. The temperature at which gas particles have no volume. Remember, the gas particles themselves have negligible volume. We talked about this with kinetic molecular theory. Have negligible volume, meaning next to nothing, all right, as compared to the space in between them. When you slow the gas particle, when you have no energy available at all to those gas particles, and they just basically fall down to the base of the container, the volume that they take up is next to nothing, all right? So theoretically, at 0 Kelvin, where there's no energy, the volume of a flexible container is 0, okay? So anyway, volume and temperature are directly proportional. If one goes up, the other goes up. The person who studied this relationship between volume and temperature in a flexible temperature or a flexible container, another Frenchman, and his name was Jacques Charles, and this is known as Charles' law. Volume and temperature, again, this is Kelvin temperature, are directly proportional. And again, this is in a flexible container. All right? So it's basically the same relationship as Gay-Lussac's law. However, Gay-Lussac's law involves a rigid container. Charles' law involves a flexible container. So let's look at it. So here again, we have, just throw a couple of particles in there, and we'll give them one bar or one tail of speed and one collision apiece. So this was, the temperature was lower, and so the volume, of course, is lower. When we increase the temperature now in a flexible container, the volume increases. So we're showing an increase in the size of the box. Because of that, same number of particles, but as they're moving faster, so we need to throw in an extra bar there or tail of speed, and the collision rate increases, so we're going to throw in some more collisions. When you do that in a flexible container, all right, The increase in those collisions on the inside walls of that container are forcing the container to expand. All right, to expand. Okay? That is Charles' law. So if you noticed, we looked at 4 relationships, 4 laws. 3 out of the 4 were direct. All right, 3 out of the 4 were direct. Avogadro's law, Gay-Lussac's law, Charles' law, all involved a direct relationship between 2 variables. The only one that's inverse, which remember graphs of hyperbola, was Boyle's law. Volume and pressure are inversely proportional. So these gas behavior relationships are known collectively as the gas laws. There are a couple more that we're going to get to later on down the way. These are the 4 main ones right here. Important things to know about temperature, okay? Gas behavior is dependent on the Kelvin temperature scale because remember, at 0 Kelvin, there is no energy, meaning there is no particle motion, all right? And so based on that, as we said with Gay-Lussac's law and Charles' law, there's either going to be no pressure or there's going to be no volume at absolute 0 or 0 Kelvin. Standard temperature on the Kelvin scale is 273 K. It's 0 Celsius, which is the freezing point of water. So to go from Celsius to Kelvin, we add 273. To go from Kelvin to Celsius, we subtract 273. So 0 Kelvin is actually minus 273 degrees Celsius. And if you throw that into Fahrenheit, it's about minus 459 and some change. All right? Pretty dang cold. All right? Pressure. Gas behavior can use any pressure measurement as long as the unit remains consistent from the initial to the final conditions. For example, if our initial pressure measurement is in atmospheres or ATMs, then our final pressure is also going to be measured in ATMs. And recall, we talked yesterday that standard pressure has various measurements based on the unit. 1 ATM, 760 millimeters of mercury, 760 torr, 29.92 inches of mercury, 101.1 or 101.3 kPAs, 14.7 PSIs. There's a bunch of them. All right. But the key here I wanted to make sure you're aware of, as we just explained, is that the temperature scale involved with gas behavior is the Kelvin scale, or it's also called the absolute scale. So, big day today, learning the 4 gas laws and the 4 relationships involving gas behavior, which could include number of particles, pressure, volume, and Kelvin temperature. Tomorrow, we are going to continue on and look at some mathematical relationships that we've discussed right here and do some math work with these 4 laws. Hate to tell you this, terrible news, there is no homework assignment for tomorrow. What did I just hear? A roar in the crowd, a standing ovation? Probably so. Well, enjoy your night off, all right? And we'll hit it hard tomorrow, promise you that. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe, keep working hard, and stick with it, all right? See you next time, guys. Take care.